Hello class, how you doing? Welcome to NMATB. Today we'll be discussing the wave equation, or we'll continue with our discussion of the wave equation, which we started covering yesterday. We were studying how to derive the general solution to this problem. We stopped at a point, we didn't quite finish everything on Monday, so I'm doing this here. And for those who didn't attend class, you get to the benefit of seeing how to get to the point or using the separation of variables. And those who had some questions, hopefully that I didn't address in class, hopefully you will see I'll be able to address them here. This problem here, along with the boundary conditions, defines or describes a string. You're given a string and you stretch it from point 0 to point L, right? Sorry. You're given a string stretched from point 0 to point L, and given some initial position of the string. U, by the way, is the displacement of the string from 0, from the initial 0 when it's flat, and x is the distance along the string from 0 to L. Now, given the initial position of the string, so given at time t equals 0, some function f of x. So imagine I had this function, which kind of looks like a sine function. I could give you a function that looks like a triangle or something. Whatever that initial shape is defined by f of x. Given the change in the displacement with time, which is like the velocity of the string, given it as a form g of x, and given this constraints that the string does not move away from this position and this position. In other words, at x equals 0, the string position displacement is 0. At x equals L, it's 0. Given these conditions and this linear second order partial differential equation, I want to find a general solution. Okay. So to start, we were employing some technique that I mentioned to you that is, pretty useful. Doesn't always work, but works for most of the important problems we'll be looking at. So for this one-dimensional problem in x, and that's a function of time, I want a form u xt equals x times t. The idea is to separate this into a function of x and a function of time, and hopefully when I play this out, it simplifies my partial differential equation to a set of ordinary differential equations. You've seen how this works with the example problems I showed in class. Here again, del squared u del x squared is just simply t, which is a constant in respect to x, times d squared x dx squared, and del squared u del t squared is just simply x times d squared t dt squared. Okay, if I use those substitutions and throw them in there, I have that alpha squared t d squared x d x squared equals x d squared t dt squared. Okay, then I go ahead and say that, you guys remember these boundary conditions, I'll come back to it. I'll go ahead and say that, or group the terms, and that gives me 1 over x d squared x dx squared. I mentioned the other day that I would rather put the alpha squared on this side. I have 1 over alpha squared t d squared t dt squared. And because this is a function of x and this is a function of t, the only way they can be equal is if I set them equal to a constant. Is that clear? Looks like. And I choose that constant to be negative lambda. Okay, somebody asked why negative, and I was showing, and I guess I will show that now. let's start with lambda and you see what the end result is. Oh, let's use a general lambda. It could be negative, it could be positive, it could be 0. Okay. So what this tells me is that I have two partial differential equations, or two ordinary differential equations to solve. One is d squared x dx squared equals lambda x, and the other is d squared t dt squared equals lambda alpha squared t. Okay, this is the same equation we've solved so many times now. The characteristic equation is d squared equals lambda, which means x is c1. If lambda, d squared equals lambda, which means d equals square root of lambda. If lambda is positive, then square root of lambda is a real number, positive number, and that's c1 e to the root lambda x plus c2 e to the negative root lambda x. If lambda is negative, so this is for positive, lambda is negative, I have c1 cosine root lambda x plus c2 sine root lambda x negative lambda. Okay, and I had mentioned in class that you have to choose this one purely because of this condition that we expect the string to be fixed here and here. So there's no way this would work, right? I just mentioned it in class and I didn't explain why. But you can see clearly from here, if I plugged in x equals 0, well, I'll do that right now. Wipe this off. If I chose let's pick the first equation. The first equation, if I chose x equals 0, x equals 0, the function x is c1 plus c2, and that has to equal to 0 from the initial condition. How do I know that? I'll take a step back right here. I mentioned in the class, but for those of you who don't remember, because u0 t equals x 0 tt equals 0, just the boundary condition at x equals 0. This can only equal to 0 if this or this equals 0. This being equal to 0 gives you the trivial solution, so we don't want that, because if t of t equals 0, then u is always going to be 0 at any given time. Rather, we want x of 0 to equal to 0, otherwise we have the trivial solution. Okay, so for that reason, we work with a boundary condition x 0 equals 0, and the same way you can show that xl has to equal to 0. Okay, so now going back to this equation here, if I plug in x at 0, I get c1 plus c2 equals 0. It tells me c1 equals negative c2. Okay, plug in x equals l, I get, now since c1 equals negative c2, I'm going to write this as c1 e to the square root of lambda x minus e to the negative root lambda x at x equals l, which is c1 e root lambda l minus e root lambda l. And the only way, again, I want this to equal to 0. Clearly, these two functions it's not always going to equal to 0, right? The only time these two functions will equal to 0 is if L equals 0, in which case this is just e to the 0, 1 minus e to the 0, 1, or if square root of lambda equals 0. In other words, if lambda equals 0, and we had said that lambda has to be greater than 0. I guess I didn't show you the case of when lambda equals 0. I'll show that in a second, but lambda cannot equal to 0. Believe it for now. So this cannot work for this boundary, for the boundary condition. This form here cannot work for the boundary condition for the reason that we just showed now, because it will never yield this shape. Okay, so that's why I said this has to hold for these conditions to be met. Okay, and this happens in every, you should always try and evaluate that. I don't know if your textbook, where am I don't know if your textbook covers that, but you should always evaluate it before determining what sign. So good question, I think Wilson. Okay, so now we're using this form and we want to apply the boundary condition. You get that C1 cosine 0, which was 1, has to equal to 0. Okay, and we've done this before. XL applied to x, change x to L in this function, because C1 equals 0. I get C2 sine root lambda L equals 0. And that is only possible if root lambda equals n pi over L. And we ended up saying that x of x of this form is a solution to the first ODE that I just wiped off. And because it's a solution, a linear combination of all the different n's is also a solution. Okay. And remember again, because it's the eigenfunction to the Sturm-Liouville problem that I just wiped off, it was x prime equals lambda x. Because it's a solution to this eigenvalue problem, to this Sturm-Liouville problem, these functions are orthogonal, as we saw before, and we can set up, using orthogonality rules or the orthogonality trick, any function, determine the coefficient using that orthogonality trick. And I will show you that in application of the initial condition in a second. So x is of this form, right? And because we know also lambda is n squared pi squared over L squared, right? Well, we said lambda was negative, so lambda n, negative n squared pi squared over L squared. Then we can solve the time function. The function is dependent on time only, right? And that gives us that, again, using the characteristics equation. Let me just write that up here again. D squared t dt squared equals negative n squared pi squared over L squared alpha squared t. So, right, so d in this case is n pi alpha over L I. So we have sines and cosines again. T is call this one d1 sine n pi alpha over L t plus d2 sine cosine n pi alpha over L t. Okay. Now we can write our full function uxt as x times t. And that is just this. That is just the summation of n to 1 cn sine n pi x over L times this. Okay. So we have a full form for u. And all we need to do now is to apply our initial conditions. And actually, let me just group these constants. Call Cn times d1 an, right? And call Bn Cn times d2. Okay, so now uxt equals summation n equals 1 to infinity, sine n pi x over L, an sine n pi alpha over lt plus bn cosine n pi alpha over lt. Okay, we apply the initial condition that u x0 equals f of x. That tells you that when I plug t equals 0 in here, that's 0. So u x0 equals summation n equals 1 to infinity sine n pi x over L 0 plus bn. Okay, and this has to equal to f of x from the initial conditions. And then we had said again, because this is an orthogonal set of functions, we can expand to f of x is this. Because it's an orthogonal set of functions, we can determine this b of n using the orthogonality trick that we've used all semester. B of n is f sine n pi x over L divided by the norm of sine n pi x over L, square norm, and this is just the integral f of x sine n pi x over L dx divided by L over 2. Alright, I'll just call it 2 over L here. I'll leave it as this for now. Okay, so we have our expansion for Bn. Remember, we have a second condition, so that should allow us to determine other set of coefficients an. So ux of t was summation an. An was with the sine n pi alpha t plus bn cosine n pi alpha over L t. So if I find the first derivative of that with respect to time, I get, and evaluate this at t equals 0, I get sum of n equals 1 an cosine n pi alpha over L t times n pi alpha over L plus bn, or minus, because the derivative of cosine is minus sine, n pi alpha over L t times n pi alpha over L, evaluated at t equals 0. Okay, and that gives you at t equals 0, this is 1, so I have an n pi alpha over L minus 0 times the sine function that is out here that I forgot, times sine n pi x over L. Okay, so we have another Fourier sine series, and because we know sine n pi x over L gives you an orthogonal set of functions, I can do the same trick. So this is g of x. I'll rewrite that here. G of x equals summation n equals 1 to infinity an n pi alpha over L sine n pi x over L. Okay, so the trick leads to gn or an to be equal to, actually I'll just write an n pi alpha over L, right? This term here is the coefficient of the Fourier, the coefficients of the orthogonal set. So this here is what is equal to g sine n, the inner product of g and sine n pi x over L, divided by the square norm of sine n pi x over L, which we had already said was L over 2. So this equals 2 over L integral 0 to L g of x sine n pi x over L dx. Okay, so we have our two coefficients, and I can take this constant over here. We have our two coefficients, so we can easily determine u of x. So I'm just going to write bn right here. Bn is this 2 over L times this, and an is this 2 over L times L over n pi alpha. So that's going to be 2 over n pi alpha 0 to L g of x sine n pi x over L dx. We have our two sets of coefficients, and we have our general solution u x t equals summation n equals 1 to infinity an sine n pi alpha over L t plus bn sine cosine n pi alpha over L t times sine n pi x over L as our general solution. Everything has been determined from the boundary conditions now. We have our an and our bn as this. Okay, so this here is the full solution of our wave equation. So now you see an application of eigenfunction expansions, application of Sturm-Liouville problems, because we ended up having two ordinary differential equations from our partial differential equation after we applied the separation of variables technique. What does this function tell you? Well, that's, I guess, what we'll talk about tomorrow. You can study this function and see the different kind of, based on the behavior of this this part here, and also because you know that you have a sinusoidal function with a known periodicity. In other words, if I have the first term of my series solution, my Fourier series solution, is sine 0, which is n equals 0. Well, n equals 0 is 0, so that I'm going from the first one. N equals 1 is sine pi x over L, and that has a periodicity of sine pi x over L has a periodicity of 2 pi over this, right? So that's 2L, right? 2 pi over L. So its periodicity is 2L, which means that my first function looks like this. The second function has a periodicity of, because the second function is sine 2 pi x over L, has a periodicity of t equals 2 pi over L. So that's just L. So the second function looks like this. Okay. Third function has a periodicity. You can keep going on to find out the different modes of this function, of this wave equation. They're called different modes. There are n modes, and these modes have different periodicities depending on what. That's a function of n as follows, right? T equals n 2 pi over n pi over L. So that's L over 2L over n. Okay, we'll continue from this tomorrow. There are other things I wanted to talk to you about for the time dependent part and the x dependent part. Other than that, we can also solve a few examples for given initial condition, we just gave you an arbitrary function f of x and an arbitrary function g of x. If I'm giving you an actual function that you know, I know the shape of my string to be maybe a sine function or something like this, or whatever form the initial condition, can I determine the final solution? We'll look into that next class as well on Wednesday. So please take this, take your time, watch this, replay it as frequently as you need to get the whole idea together. And we'll look into this a little bit further tomorrow. Thank you.